Hi and welcome back to another LeetCode video. We're looking at LeetCode 42, trapping rainwater. It's marked as a hard problem, but once you've solved it, you may find it much easier. So let's see what we're dealing with here. So we're given n non-negative integers representing an elevation map where the width of each bar is 1. Compute how much water it can trap after raining. So this is the elevation map. The black boxes are the blocks, and the blue ones is the rainwater that it would trap. Okay, let's see what are the constraints. Well, so n is the length of our height array. We have at least one element in it, and the heights vary between 0 and some positive number. Okay, cool. So yeah, let's have a look at this example. So 0, 1, 1. So that's really just the height map. And well, let's walk through this because it's maybe not that easy to see right away what the solution is. So that's why we want to work through the example to get an idea of what an algorithm could look like. And I would suggest we start iterating from the beginning of the array to the end of the array and see if we find anything that we can remember to then compute how much water is going to be trapped. So my first observation would be that if we go from left to right through this height map, we see that, we kind of have to remember the height of a previous block. And then when we run into a higher block, we know that, okay, there's water going to be trapped here, but not up to the height of the new block. Instead, only to the height of the previous block, right? So we can see this here, and then we have a higher block. And maybe now we start remembering that height as well. We go over this block of height 1, then we have here height 0, then we have height 1, and then we run into height 3. So now, again, we need to take the minimum of these two peaks, right? And then compute how much water is between those two peaks. And similarly at the end, we need to do that as well. So here, what do we have here? Well, we have a high peak, but then we start iterating, but we don't find another high peak in this area that is the same height or higher than this peak, right? So that means that we can't just fill this portion with water. So I guess the first observation here is that we remember a peak until we run into a new peak. And all the water that we found that could potentially be in the valley between the two peaks, we have to remember that as well. But only when we find the next peak can we actually count it as trapped water. And I think that's the way to go. So let's try this with this example. So we have height 0 here. 0 means, we don't have a previous peak, right? So we're not trapping any water. We're not potentially trapping any water when we go from the block at position 0 to the block at position 1. Now, when we go to the block of, so 1 is our new peak. So now what we do is we go over this block of height 0, and potentially we have 0 minus 1, so the height difference of the two, that could potentially be trapped water, but we don't know until we run into the next peak. So then we take a further step and we see that, okay, now there's a new peak. We have 1 unit of potentially blocked water, and we can book that, right? So that's guaranteed to be trapped rainwater. And now we start from the beginning, essentially. We set our new peak to the height of 2. We go to the next position in our height map. And now the difference between this block and that block is 1. So we are adding 1 potential unit of blocked water to our memory. Then we go to the next position. Now the height difference between the peak and the current block is 2. So we're adding another 2 potential blocks of trapped rainwater. Then we do that with here. And now we have 4 blocks of potentially trapped rainwater. And then we reach a new peak. So that means we can now add these 4 to the one that we had before. That's guaranteed to be trapped rainwater. We are now at the new peak, and we continue the game. So here we have one potential block of trapped. Here we have two. Here we have another one. Here we have another two. But now we've reached the end of the array, which means we cannot add this potentially trapped rainwater to the actually trapped rainwater, right? It doesn't count. So we're going to discard that. Now, that is only the first part of the algorithm, I think. So that is what we're going to implement. But we also need to get this block. So how do we do that? Well, in every height map, right? If it's like a valley, it's easy to compute all the water between the two peaks. But if you have like kind of like a mountain where you have one single top peak, you also need to do the same procedure from the other end. So at the very end, after we've processed the array once, we actually need to go from right to left to do exactly the same thing until we reach our peak again. Because we know that everything after it will just be potentially stored rainwater, and then we're never going to add it because we never run into another peak that is as high or higher than our current block. Let me correct this. We're not going to run into a peak that is higher than the current peak. If we had a peak of height 3 here, all of this would be trapped rainwater where it's currently a white. But when we do a back pass, it would also be potentially trapped rainwater. So we would count it twice. So on our way back, we actually have to just go to the last highest peak in the array, right? In case there are multiple peaks of the multiple highest peaks. So yeah, that describes, I think, the whole algorithm. It's a linear time and constant space, because we only need to keep track of potentially and actually trapped rainwater while we iterate through it. Yeah, we need to be a little bit careful to implement it in running into both directions, but that's implementation detail. So with that, I'm going to start to implement this now. O of n time and O of 1 space. We're going to say trapped rainwater in the beginning is 0. And we are going to have a variable with potentially trapped rainwater, right? Trapped rainwater. And I'm just using these variables just to make this a little bit more clear. You might want to choose different ones if you encounter this problem in an interview, just to make it a little bit easier to write the code. So yeah, so what we're going to do is we're going to iterate over all of the elements for I in I and height in enumerate heights. I'm going to change the name heights. I'm just heights. Cool. And yeah, and we need to remember what the previous peak was. In the beginning, it's 0. We just assume it's somewhere here. We know that all the height values are between 0 and some positive number. So the previous peak, if we set it to 0, we're not going to have a problem with that. And we're going to compute the height difference. So we have height minus previous peak. And if the difference is, well, let's height ht. Well, let's take the previous peak minus height, so that because we want the difference, if the difference is larger or equal to 0, that means we can add our potentially trapped rainwater to the actually trapped rainwater, right? So we'll have trapped rainwater plus equals that, and then we're going to reset our potentially trapped rainwater as well. Cool. Now the other case is if the difference is smaller than 0, that means that we have a peak and the current height is smaller than the peak, then we have to add the difference to our potentially trapped rainwater. That's all that is. But because the difference is negative, we have to add it to, in order to add it, we have to subtract it or make it negative. Or let's say like this, plus equals minus. Right, and now what we also have to do is we have to remember the new peak, right? So previous peak is going to be height. That's pretty much it. And yes, maybe we should call this height difference. Height difference. There you go. Cool. Let me just step through. Well, we can step through this in a second. So that is the first part. That is the left to right processing. Now at the very end, we might have some potentially trapped rainwater, right? But we can't really use it. So, and now I said we want to go back to the previous highest peak. So what we do now is, well, we need a for loop that goes backwards. That's pretty much it. Or we could put this into, well, a little helper function for us, and then call that again. I don't think I have done it. I think I have done this where I just have, because you can see I've solved this problem before. Yeah, let's just iterate traditionally just backwards. We're just going to have another loop here. Now, we have to remember what the peak element is, right? So height max equals the previous peak, and it's guaranteed that the previous peak is non-decreasing as we iterate through this array, as we update previous peak in the first iteration. So what we'll do now is here, we will just check if height equals height max, we're going to break out of our for loop. That means we're going to terminate when we find the previous, well, when we find a peak that is as high as the highest element in the array. We could also just say max height. Heights. That's the same. Cool. Now, let me see. We actually don't really care anymore. Enumerate heights. Well, we're going to change this for range, length, heights. So now that it's actually correct. So we're just iterating over the height. We don't need the index I anymore. Actually, we also didn't need it here, did we? In heights. We could use the index to remember where the last peak was, but just knowing what the maximum, well, what the height of the highest peaks is sufficient enough. So yes, I think that is it. But we have to run through the code with our mental debugger once. And I'm already spotting one problem. We have to reinitialize our potentially trapped rainwater with 0, of course. Let's see. Cool. So let's use this this example. So we're getting a height of 0. The difference is 0. So it's the same with the potentially trapped rainwater is also 0. So we're adding nothing. We're actually resetting, and our current peak is 0 again, right? Next, we run into height 1. That is this if case. The height difference is now negative. Height difference between previous peak and current height is negative. So, oh, I see. So there might be a problem here. Is there? Yes, there's a problem. I think the logic is switched. So if the height difference between the current peak, maybe we should do it like this, just to make it a little bit easier to read. So if the height is larger or equal than the previous peak, we have to add the already potentially trapped rainwater to our actual rainwater. We have to reset our potentially trapped rainwater, and we have to update our previous peak. If it's not the case, we're going to increase the amount of potentially trapped rainwater, and that is equal to our previous peak minus height, isn't it? Because we know previous peak is larger than the current height. So that's what we're going to add to our potentially trapped rainwater. All right. So at 0, we are in this situation, but we have no potentially trapped rainwater, so nothing has changed. Now we run into this scenario again. Potentially trapped rainwater is 0, so nothing is going to change, but we're going to set the previous peak to height 1. Then we run into a height of 0 in the next loop iteration. And now what we have is previous peak is larger than height. So it's this else case. And since it is larger by 1, we're actually going to increase our potentially trapped rainwater variable by 1. That's fine. Next loop iteration, we run into this case where we have the height 2. So that is this case again. That means our current height is larger than the previous peak. Now we add the potential trapped rainwater of 1 to our result variable. We reset the potentially trapped rainwater and we remember the next peak. And then the next 1, 2, 3 steps is all this case where we add 1, 2, and 1, and then we run into the peak here. And we're adding again our potentially trapped rainwater. And yeah, and the rest of the loop is we will never run into another higher or peak of the same height as before. So this part will never get executed for the remainder of the array. And we're only adding potentially trapped rainwater, but we're going to not use it in the end. Right. So now we go the other direction. And here I'm going to use the same logic. Let me just transfer the changes that we've made here. And that is this. And while we add it, I'm also going to just change max height to max peak. Max peak. Yeah, and because the logic is exactly the same, it also works exactly the same. So we start here, our previous peak. Oh, I see. We have to set our previous peak as well. We have to set it to 0. Otherwise, we're going to have an issue. So that's why you run through your code, so that you find these things. I'm just going to do that. Yes. Now it's a little bit more. Maybe a little better to read. I don't know. So, okay, so we're iterating over the heights array in reverse order, but this, of course, doesn't work. So we have to do height equals heights position I. Or what we could do, we could just do it like this. Just do it in reverse order. So now we're iterating in reverse order over the heights. So in the beginning, our previous peak is 0 because we start from here. We have no potentially trapped rainwater. We iterate backwards through the array. First height is 1. It's larger than 0, but we have no potentially trapped rainwater, so nothing changes really. We're going to remember the 1 as our previous peak. Next step, we run into this case of the if statement again. We have a new higher peak. Again, we have no trapped rainwater, so nothing is changed in the result. But we are updating previous peak with height. Next, we run into, that's the only time where we run into the second case where we add 1 unit of potentially trapped rainwater. And the next loop iteration, we run into this case again. So that means we're actually adding this 1 unit of potentially trapped rainwater back to our result. Reset the trapped rainwater to 0, and the previous peak remains the same. And then finally, we run into this case where we encounter the next peak. Again, it's this case of the if statement, and we have no additional rainwater that was trapped, so nothing changed in the result. and we're updating the previous peak to height, and then we run into this. So if height equals max peak, which we've remembered before, then we break. So that's it. And it's important that we break out of the loop after we've handled this case, right? So yeah, I think that's it. And we ran through the code once to debug and with an example. That should give us enough confidence that we did everything correctly, unless we were blind and just didn't see something. So let's see if that works. All right, so test cases pass. And now I'm going to submit this. And very nice. So that's the solution. Yeah, so if you want to try this yourself, I recommend just understanding this, then looking away and trying to implement it on your own. It's always a better practice if you understand something, and then when you try to reproduce it, to not look at the answer, only when you get really, really stuck. Anyways, thanks for watching.